How many of you are mildly jet lagged? Okay, good. Yeah, mild might be, it's a spectrum. It's not a Koopman spectrum, but it's a spectrum. Okay, good. So any burning questions from the first part of the day that anyone would like to get off their minds? Or should we just roll in? You decide. If anyone has any burning questions, you can think about it. You should have burning questions. Good. So a little bit of history. And I don't know if Igor covered any of this, but there is actually a very, very rich history and a little bit of intrigue surrounding Koopman theory in the 1930s. So it turns out that Koopman's operator theoretic perspective was the missing piece, kind of the missing puzzle piece to solve Birkhoff's ergodic theorem, to kind of tie this up, right? So we know how the statistical theory of gases works, that you can do kind of space or time averages and that they should be equivalent in some sense. But there was a little missing piece that Koopman's paper tied up with a bow. It was very, very quickly generalized by Koopman and von Neumann the next year. Now, what's interesting was there's this great review paper by Calvin Moore. I don't know if this is, 2015, something like this. But it turns out that essentially a prominent mathematician at the time in the US saw von Neumann's talk, was an editor of a member of the National Academy of Sciences, held up his paper so he could write his own self-invited paper and tried to scoop him. Not knowing, this was, I think, von Neumann's first paper in English, not knowing that he would become one of the greatest mathematicians ever to live and very prominent. So I think this is a very important cautionary tale. You should treat young people very well, and you shouldn't assume that you can push people around and ever take advantage of that kind of privilege. It's just a shitty thing to do. But also it, definitely came back to bite that mathematician who at the time was the most prominent applied mathematician in America. So read this paper, very interesting, but a very good cautionary tale for us today. Okay, and this is the paper that I left out of my earlier linear DMD history. But before Clancy and Igor's paper, there was about a 10-year paper trail starting from Igor's thesis through now that essentially built and generalized on this kind of Hamiltonian idealized Koopman world into the more dissipative non-Hamiltonian world, which is where we live as engineers. So that's a huge and important kind of departure that was largely led by Igor. I think it was lonely for a while, probably, is my guess.
It's pretty lonely.
It's pretty lonely. Now he's got lots of.
Tony watched some of this.
And there's another kind of parallel literature that I'm sure you'll hear lots about, which is the kind of dual side of this, the Perron-Frobenius side. How many of you have heard of Perron-Frobenius? Pretty much most of you, right? Which again has its own massive literature and massive history that was largely in parallel until they became kind of more merged in the data-driven world. So Gary and Catherine and others led that. But importantly, right, the way that we've computed these things has evolved tremendously over the last, I guess, 15 or 20 years or so. So the way we actually compute these things has evolved quite a bit. So I'm going to talk just a little bit. We wrote a paper a few years ago. We actually wrote it during COVID, but it got published a few years ago, which was essentially a review paper, mostly from the engineering applied math perspective of how useful these techniques are, different perspectives that you can take, and how to think about it. So this is one of my favorite dynamical systems. It's just the double well potential, very minorly nonlinear system, right? You just add a little cubic and your life becomes more interesting, or a quadratic. And the traditional view here is that you would locally linearize around your fixed points. This is the geometric view of dynamics from Poincaré that we've all been taught in school, is that you find your fixed points or your periodic orbits and you linearize. You look at the unstable and stable directions to build your manifolds. Maybe you get, homoclinic or heteroclinic connections and you build your topology from these kind of basic elementary geometric pictures. But from an engineering and control perspective, my ability to work in a linear space is very limited to a small neighborhood around my fixed point. Good. And so I think the first thing that was very appealing to us is this idea that you can work in a much larger linearized neighborhood with these kind of more sophisticated nonlinear coordinate transforms and embeddings. But again, I want to be very careful. Your local linearization, let's take this blue region or this pink region around domain 1 or domain 3, these two fixed points. You can naturally grow your domain of linearization. You can apply coordinate transformations to make your system look linear in a larger and larger domain until you hit another fixed point, like this saddle point in the middle. At which point, as Igor pointed out, x dot equals ax does in fact have one fixed point at the origin, and it is not possible to represent, at least locally, in natural coordinates that map to the original coordinates, of interest, until you hit another fixed point or another kind of topological structure like an unstable periodic orbit. But that still gives you great flexibility in having a much larger area where you can do design, optimization, and control using linear techniques. Okay, this is what we call the local perspective of Koopman because it's about local linearization and expanding the radius of local linearization. Now, how many of you remember normal form theory in dynamical systems? This is a big deal in the 80s, the 90s, when I was learning this in the 2000s. This should resonate very, very much with you if you remember normal forms. What normal forms do is they start with a local linearization, and then you find near identity transformations, simple, small transformations that push out the nonlinear terms farther and farther, that kill as many nonlinear terms as possible and expand the radius of validity of your local linearization. We've been using this for space mission design since the early 2000s. And that's morally very, very closely related to what we're doing here. Okay. The other perspective is what we would like to call the global perspective of Koopman eigenfunctions, which is, this is I think, we were careful in choosing this example. This system has a well-defined energy function, right? There's a potential energy landscape given by this double well potential. And the energy itself is a Koopman eigenfunction. ddt of any conserved quantity is 0 times that conserved quantity. So linear momentum, angular momentum, Hamiltonian energy, these are Koopman eigenfunctions. And your level set tells you a lot about where you are, just like Igor was saying. Your energy and phase are very important quantities. But importantly, if I know that I am on this red level set, it tells me a lot of information, but it does not tell me if I'm in the left or the right lobe. So I lose some local information in this global view. And I think this might be what Igor is saying is, yes, in fact, there are x dot equals ax can represent a system with multiple fixed points, but you have some collapse of information, some symmetry where you lose some information about are you on the left lobe or the right lobe. And so there's no free lunch, and we just have to be very cautious about what we expect to be able to do with these representations. This is fundamentally different than this. They're both useful, but they're different. And then there's more of the signal processing perspective, which is, if I'm in this kind of red right region and I have these, cat's eye looking orbits, morally what we're really doing is we're kind of linearizing and circulifying these orbits into something that's a little bit more well-behaved. Okay, this is kind of the engineering picture. Anyway, so this paper discusses how to find effective coordinates, how to extend to multi-scale dynamics, continuous spectrum, and especially how to have robust numerics. Importantly, this was actually before we learned a lot about Matt Colebrook's recent extensions. And so I think there are a couple of major extensions that go beyond what we talk about here. Okay, so I alluded to this briefly, that there is this PDE that you can use to solve for Koopman eigenfunctions. So I don't actually want to lift to infinite dimensions and then collapse. I just want to find the eigenfunctions. That's all I actually care about. I want the best, most underdamped or undamped eigenfunctions, the one that persists the longest. That's what I want. And I want that from data. So if I have a dynamical system, what I'm really looking for are these eigenfunctions phi, so that phi dot is lambda phi. And of course, I can use the chain rule, and I can expand this out. So dt of phi is grad phi times x dot, which is just f of x. No big deal. And that, of course, equals lambda phi. So this is my PDE for Koopman eigenfunctions. A Koopman eigenfunction will satisfy this PDE. Now, any numericist who's played around with this, I showed this to my PDE buddies, and they're like, this one is terrible. You don't want to solve this. It's not a nice one. But, you know, for simple 1- and 2-dimensional problems like x dot equals x squared, this is exactly what you would use to find, you know, the Laurent series for this eigenfunction. You literally plug in x squared here, and you'd compute grad of phi, and you'd balance all of these terms, and you'd solve for the coefficients. So you can do this, but it's not very robust or scalable. But this actually does help us understand how would we numerically approximate these phis from data, and how would we extend this framework to control. So that's what I'm going to tell you about now. Any questions? Okay, so this is work by Ulrike Kaiser when she was a postdoc at University of Washington. She was my first postdoc all the way back in 2014. And the idea is we want to extend this idea of kind of the Koopman eigenfunction perspective of this local linearization to systems that are not just autonomous dynamical systems, but they also have external forcing and control, plus BU. So if you're not familiar with control theory, the whole idea here is that you have some dynamical system, x dot equals f of x. That is the world you observe. And you add some intervention, some plus BU that you have control over. You can specify u of t to modify the system to whatever engineering objective you have. Maybe you're trying to suppress the spread of COVID or malaria. Maybe you're trying to stop people from having seizures. Maybe you're trying to regulate the global financial markets or stabilize the flow over a wing. Okay, control is a very central part of our world. It's one of the main reasons we want to characterize dynamical systems, and it's one of the main motivations for having linear representations of them. Okay, so I'm going to break this into a few things. The first bit is purely from data of the autonomous system without forcing. We are going to discover eigenfunctions from data. We're going to approximate these eigenfunctions from observational data of the unforced system. Then what we're going to do is we're going to incorporate control into that linearized Koopman eigenfunction model. So this is my kind of linear Koopman eigenfunction model, phi dot equals lambda phi. And this is how control enters. And it's extremely straightforward. You literally can just do the chain rule of this, and instead of plugging in f of x here, you plug in f of x plus bu, and you pick up this extra control term. It's a state-dependent control on an otherwise linear autonomous system. And then you can do control design on that new system using relatively straightforward methods. We have state-dependent Riccati solvers that are built into every modern control toolbox. Okay, everyone okay with this pipeline? So this is very nice. This shows that you can characterize the unforced system. This is just like vanilla Koopman. And then you can add control in a very natural way and do the control optimization. Okay, so how would we start to approximate these eigenfunctions from data? The basic idea, what we tried to do earlier, remember with those polynomials, was what we tried to do is pick some basis for our Hilbert space, some truncated basis, And we tried to expand our eigenfunctions in that basis set and learn the expansion coefficients. That's how we do all function approximation. Okay, and these slides were made, I guess, probably back in 2014. We in the community have connected. There is, of course, decades and decades of deep literature into approximation theory that is getting much better connected to Koopman theory in the last 10 years or so. But the basic idea is we're trying to expand phi of x in this basis and learn the coefficients xi that best approximate that Koopman eigenfunction. Good. And so you can essentially build this as a matrix regression problem, just like DMD that I showed you earlier. That's where we're always going to go. We have bomb-proof numerical algorithms for linear regression problems. So we want to pose everything we possibly can as a generalized linear regression problem. And then if that doesn't work, you relax it into a neural network, but at least you know what that neural network is approximating. And so you can essentially build a data matrix for theta. It's theta evaluated at your first point x1, your next point x2. These are just theta evaluated at your data, data on data. And then we define this gamma object as essentially this grad phi dot f. I think that's what it is. Yeah, grad phi dot f. If you have access to your governing equations, f, use f. If you don't, then approximate x dot. They're the same thing. F and x dot are, f is a model of x dot. So you can also build this guy with data. And of course, grad thetas, these are analytic functions you chose. You know what grad thetas are. And so now I can essentially build a linear regression problem where I'm trying to solve for these coefficients xi in the null space of this object. Now, obviously, the simplest least squares solution of this is xi equals 0. So that's why I say, instead of just solving this set of equations for xi, what I'm really trying to do is I'm trying to solve for a xi in the null space of this object. That is the object that we actually want. And this was when we were really excited about our algorithm Cindy, so I called this a generalized Cindy regression, but really it's just a linear regression problem. How many of you have heard of our Cindy algorithm? Who has not? I'll briefly introduce it later, but this is probably a stupid name, but basically we developed some algorithms to find a vector in the null space that has nice properties. Okay, now the nice thing is in discrete time, when my data x1, x2, x3, x4 are discretely sampled snapshots of my system at delta t intervals, sampling intervals, this matrix regression problem reduces to the extended DMD developed by Williams or the VAC algorithm developed by Noe and Newski a little bit earlier. So these are well-known algorithms that generalize DMD to nonlinear systems. So now we can actually get a nonlinear function expansion of a proper nonlinear object phi using a DMD-like regression. Okay. Importantly, the main thing is you can build these data matrices purely from data. These theta and theta prime matrices purely from data. Okay, everybody with me? This is obviously a little messy, but like the big picture here is that this is a matrix system of equations. I can build these with data, and then I can solve for the sparse vector in the null space, and I get a sparse expansion approximation of my eigenfunction. So for example, if I have this system here, my double well potential we were playing around with, maybe I'm going to do control in this double well potential, you would essentially collect data, like trajectory data in blue here. You'd collect unforced trajectory data. You would build the data matrix of theta and gamma on that trajectory set. And you would solve for the vector of coefficients xi. In this case, we want sparse vectors. They don't have to be sparse. But you would solve for some vector in the null space of this object. And that would give you an approximate Koopman eigenfunction. And bang, we learned the Hamiltonian energy function. Purely from data, you learn the conserved quantities, for example, because that is a sparse vector in this null space. It's an eigenfunction that is in the null space of this object. You can learn other eigenfunctions in the same way. A bit louder. So we don't have to add the sparsity prior. We can find a vector in the null space. That's totally fine. So you can find non-sparse vectors, but our basic idea is that if we chose a good coordinate system, usually sparsity is a nice prior to prevent overfitting and regularize. Yeah, that's actually one of the more interesting mathematical problems in my mind today. If you want to enforce symmetries or sparsity or many, many constraints, you end up getting a regression problem in a null space. But if you add a little noise to your data, your null space becomes very high dimensional and very fuzzy. So you're trying to find like an approximate null space. And there's a lot of very, very interesting algorithms that can play around with that idea that there's like, I want an approximate null space.
Here you say you can really find to achieve precision.
Yes. Yeah, we have good numerical algorithms to, within some bound, find a sparse vector in a null space now. You have to pick, but that's a hyperparameter. You can sweep through it until you find something where you're like, this is sufficiently Hamiltonian-like for me. Okay, good. So, June. Not necessarily the longer, because there's often cases where if I'm on a limit cycle, I don't actually get more information the longer I measure. What I want is a more enriching measurement, which is measured by the condition number of theta or gamma. So I want measurements that improve the conditioning of this ill-posed inverse problem, of the pseudo-inverse of that matrix. So these are quantifiable with the SVD, but it's not just measuring more, it's measuring smartly so that you improve the conditioning of these matrices. Good. Now, this is a toy example. I know how to control this system. I know what the Hamiltonian is, right? Like, we know everything. I highly encourage you, if you're interacting with a new mathematical object or a new thing where there's a lot of promise, try it on a system where you know the answer and see what it buys you. Okay? So we know the Hamiltonian, we learned the Hamiltonian, we're going to show that we can do control in the Koopman way, and it turns out to be energy optimal nonlinear control, which is very, very nice because we can generalize that to other Koopman eigenfunctions. We can do total angular momentum optimal control and things like that. Just remember though, this is my eigenfunction, and we're going to plug it into that control framework right here. So now phi is my Hamiltonian that we learned from scratch. And we're going to design optimal control U to optimally increase or decrease the energy of my system. So if I'm a little trajectory orbiting this thing, I can optimally add or pull energy out using this Koopman nonlinear controller. Okay, so you do the basic expansion, you pick up this control term, that's pretty simple. But now we can run this back through our optimal linear control framework, right? Our LQR linear quadratic regulator, but using this, this system here. And so we get a controller, and I think what I'm going to try to point out here is that we have applied it to lots of simple mechanical systems that do in fact have Hamiltonians. In every case, you can learn that. And you can use that to do optimal energy optimal control to get your system either controlling to a fixed point or increasing the energy or jumping to a next new fixed point in a way that uses the nonlinearity instead of fighting the nonlinearity. Remember that picture I showed where you have the local linearization and then the more like the bigger Koopman linearization? What you would normally do is you'd have a tiny little region of local linear validity, and anything outside of there, you'd be fighting your nonlinearity. Here, we're using the nonlinearity to do optimal energy shaping of our trajectories. Okay. This is one I thought, one second, June. This is one that this is where I finally convinced myself. We call this method chronic, because I was listening to a lot of Dr. Dre at the time. we decided to design an energy optimal controller to hop to different wells, which is a relatively challenging nonlinear control problem. Well hopping is a baby version of space mission design. So this was something I learned from Jerry Marsden when I was an undergrad at Caltech, was that, you know, if you have a planetary system like Jupiter and the Sun, we all know that there's 5 Lagrange points. But these ones are particularly interesting. These are rank 1 saddle points, meaning that there's, if you linearize them, one of the directions is a saddle and the other directions are centers. And so there is a potential energy forbidden region. Let's see if I can draw this, where we can't live here. But if I'm a spacecraft or an asteroid of a sufficiently high energy, I can, in fact, I have another color, someone over here. If I have sufficient energy, I can, in fact, and there's an unstable periodic orbit around this rank 1 saddle. These are called halo orbits because they look like halos. If I'm here, it looks like a halo around the sun. This is where our James Webb Space Telescope lives if this was the Sun-Earth system, because it's always dark. Very nice property. So if I have the right energy, I can, in fact, there exist trajectories that will come in, go around this orbit, enter the inner solar system. Now, importantly, Jupiter also has moons. And so Jupiter and its moon also have their saddle points. And it has multiple moons, moon 1 and moon 2 and moon N. I don't know how many moons, but there's a lot of moons. And so there are these trajectories that connect. It's a very complicated topology of trajectories, but these are somehow connected in a way that you can do optimal, energy optimal space mission design to, for example, go from one moon to another moon, and you can design space missions on the fly without doing a huge amount of pre-computation and without spending a huge amount of energy to do these burns. Each of these is like a little local minima in your energy, right? And so that's essentially what this is a baby version of. And if you can do this automatically by discovering an eigenfunction, plugging it into your control framework, and then learning an energy optimal transition, you can, in principle, generalize that to much more sophisticated control problems. And so essentially, kind of the unforced system, these are your energy level sets. We learn the ability to control to much, much lower energy level sets by going through these energy transitions. Anyway, big picture here is that you can take this Koopman eigenfunction perspective if you learn a couple of relevant eigenfunctions, things that have zero or slow dynamics, the most lightly damped dynamics or the most persistent dynamics. If you have a Hamiltonian, that's clearly going to be the longest time structure. If you have a damped system, just find the least damped eigenvalues, the things that last the longest, that ring the longest through your system. And you can use those to design controllers that kind of optimally use those persistent dynamics. Okay, any questions? Yes, June, sorry, I skipped your question, please.
I just want to double check. So here, you're not just finding one eigenfunction.
I actually am. In this case, I was just finding the Hamiltonian, but you can generalize this to a couple or 3 or 4, and you can control in that subspace, in that eigenfunction kind of manifold.
Is the more the better?
No. Usually your system has some timescales that are relevant, and you'll have a few slow eigenvalues that dominate most of your observed dynamics. So in the example I was giving with fluid flows, where I had that power spectrum, where my power spectrum was had a couple of peaks, I would say there's probably about 3 eigenfunctions that I need to be paying attention to, and they're going to be the ones that persist in the data the most. If I take a long time series of data, these are the ones that have the most kind of power or energy in the data. These are going to be the ones that stick around and hang out the longest and have the biggest signature in the data. And so these would be also the things I would want to control the most.
But what about your transients? Are you just assuming I don't start controlling until after the transients have died off?
That's a good question. So actually, this global picture captures transients. It just only captures them from fixed point to fixed point. Yeah. Question, yeah.
I'm wondering how this compares to like a very classical course technique that you like control. I know it's probably a lot faster. But...
Yeah, so model predictive control on the right time horizon will give you a very similar answer, but it's much more brute force. It's like a much more expensive and it won't scale as well. I think you might actually flip that and say, this will give you something that's as good as the industry best model predictive control, just very easily and almost for free. Yeah. Good. Okay, that's how control enters. At this point, I'm gonna break it into vignettes. We're gonna just do topics. That was one topic, control. I'm going to switch gears and we're going to talk about a different topic, noise. When I have real systems, I have measurement noise. So this is one of my absolute favorite papers in data-driven dynamics. This work by Shervin Bagari, who's a professor at KTH. And he very carefully characterized what happens when you have this Koopman mode decomposition for a system with small amounts of measurement noise. And interestingly, there's actually two types of noise, right, in any dynamical system. You have trying to decide what variable. You have process noise. This is stochastic forcing. And then you have measurement noise, y equals x plus measurement noise. And for any real system, you have both of these. This is often from unmodeled dynamics, from small scale dynamics that we can't resolve. So in the fluid example that Shervin was thinking about, I have my turbulent example here. All of this little stuff acts like stochastic forcing on the big coherent structures. So that's going to be stochastic forcing. But then if I actually measure the system in an experiment, there's like literal Gaussian measurement artifacts that corrupt my actual ability to measure the state X itself. Those are two fundamentally different types of noise. And Shervin and then follow-on papers did a really beautiful job of characterizing how each of these types of noise contaminate the Koopman spectrum. Okay, so for example, I should just leave this up. So for example, if I have a system, let's see if I can do this on the fly. It's going to be dangerous because I haven't read this paper in a long time. In continuous time, let's say I have a nice, well-behaved system with eigenvalues that are on the imaginary axis. This is a purely harmonic system, no big deal, okay? If I add measurement noise to the system, that bends these eigenvalues into a parabola where the higher frequency ones are contaminated more in a very predictable way. And if I add process noise, it shifts the mean. There would be a constant offset and then the parabola from the measurement noise, which is kind of amazing. It's extremely well stereotyped. And he actually demonstrated with an asymptotic expansion that this is analytically what you should get. It's not approximate. He proved that this is what you should get for a large class of systems relevant for fluids. But what this means is that if you see certain artifacts in your eigenvalue spectrum, you can diagnose them as process noise and measurement noise, and then correct for them.
With the if you remain conservative, meaning the fluid doesn't go anywhere, then even with the dynamic noise, shouldn't be preserved for zero eigenvalue.
Yes. Forget process noise. Let's assume I have a conservative system, but I have measurement noise. Then this parabola is still pinned at the origin. So that zero eigenvalue, which I didn't draw, our zero eigenvalue still remains zero. So the steady state is unperturbed.
So what was the shift? I missed what
The shift is if I have stochastic forcing.
why does the zero, I didn't understand why the zero eigenvalue disappears.
Why it disappears.
Yeah, I mean, it's not there, but just moves to some negative real.
It might have to do with the nature of this forcing. That's a really good question. Honestly, like that's beyond my ability to answer right now. It's a great question. I don't know the answer to that, but I'm sure we could dig into this. Importantly, what this does is it gives us lots of ideas of how to fix this numerically. So we do know, in fact, if we have measurement noise or process noise, how to actually debias this linear regression to fix the effect of those noise, the noise and the measurements. So this is just a very high level. We wrote about this in our SIAM book, which is massively out of date. And like this is probably, if you read it, it's comically imprecise by today's standards. But here you see regular vanilla DMD in yellow would be the contaminated version. So you can see that there's an offset because we have stochastic forcing. And then there are two versions of corrected algorithms, one that's called total least squares and one that's called forward backward. And then the ground truth is the blue dot. These are eigenvalues. These are eigenvalues of a random dynamical system where we contaminate it with forcing. Each dot, this is a good question. This either is, it's been a while, it's either a high dimensional dynamical system where there are actually 50 or 100 eigenvalues, or it is a stochastic sampling of it a few times so you get the distribution. It's probably something like that. Oh, I'm sure there's a complex conjugate part of this. This is just one, yeah, there's a complex conjugate cloud as well. We're just zooming into one of them. And so anyway, the basic idea is total least squares is pretty good. Forward, backward is a little bit better. And since then, there have been better algorithms that debias for noise and for forcing. So just something you should be aware. If you have noisy data, you will have a contaminated spectrum. It is diagnosable the extent of how much the contamination is. We actually use this to diagnose our experimental measurements, how bad they are, based on how curved our Koopman spectrum is. And you can correct them using very simple algorithms like total least squares instead of regular least squares. Yes?
Can you explain again the eta and the n?
Yeah, I mean, I don't remember. This is probably the noise magnitude, and this is probably the number of snapshots or something like that, like the amount of data m, and the magnitude of the noise is eta. So less noise on the left, more noise on the right, less data on the bottom, more data on the top. So best case, worst case, middle cases, just to compare how this algorithm works with more noise or more data. Yep. Sorry, I didn't make this figure. This is, again, something I stole from my wife, Bing. Other things that are interesting for us to be aware of. One of the limitations of DMD, again, I'm talking about the data-driven flavor of Koopman, just linear regression to find that A matrix. One of the limitations is that very often there is not one frequency that characterizes your system very well. There's not a low dimensional set of frequencies. And for interesting systems like this evolving mixing layer, the frequency actually continuously evolves in space. So if I take a window here, or here, or here, the frequency spectrum evolves, which is problematic. If I take this full data set and I run it through DMD, I'm going to get a garbage spectrum that mixes all of this. It's not going to be useful. But remember our analogy that DMD is like PCA and Fourier transform having a baby. We know that the Fourier transform is an amazing tool, but it is not the only signal processing tool we have for all time series data. Sometimes we do a spectrogram. Sometimes we do a wavelet decomposition. Sometimes we do different decompositions. If we have a purely periodic signal, we do a Fourier transform. If I have a signal like a beautiful piano piece that is harmonic but evolving, I do a spectrogram. Make sense? And so we had this idea, maybe we could build a DMD spectrogram. That's exactly what this blue plot here is. This is the spectrogram of the Koopman spectrum as it evolves spatially for this mixing layer. This is much, much more interpretable and easy to understand and work with. Does that kind of make sense?
Can you explain the spectrum?
Yeah, so the spectrogram basically is a windowed Fourier transform where you do the Fourier transform over some window of data, and then you slide that window and the eigenspectrum can continuously change. Like this is, you can literally see the transition where it goes from being a simple 2 frequencies to having more broadband. So you can kind of see this onset of turbulence happening in the spectrogram. And similarly, you could do the wavelet decomposition in time instead, or the, anything that generalizes Fourier, you can also generalize DMD in that same way.
And the window here, spatial.
This happens to be a spatial filter just because it's a spatially evolving flow. You could also do this temporally as well.
It's much finer than these large changes.
Yes, I'm just doing, yeah, sorry. It is a continuous kind of spectrogram moving average. I couldn't tell you if we're using, like a Gaussian or whatever we're using. These are just samples of the spectrogram at those frequencies.
Does the original whole space system?
Yeah, I did not plot the DMD of the original space, but it would look uninterpretable and useless. It would mix them all. It would mix them all.
This is like classical things like plot there.
I don't know. That's a good question. What I know from my understanding of Fourier transform and spectrograms is that if I took the Fourier transform of the entire signal, I would get a Fourier transform, right? This axis is frequency, that would blend all of this and be contaminated. And that's what DMD does. So it allows you to deconvolve that. Yes?
So this was systems where the exciting puts to fx that f is no longer constant function.
This is, well, okay, this is a spatial, I'm doing a spatial windowing here because different regions of space have different frequencies. You could also do a temporal windowing, like if my system evolves from a tractor to a tractor, I could have a windowed DMD and capture like the local eigenvalues that are relevant here on the trajectory, or here on the trajectory, or here on the trajectory. It's just, the idea is that you can generalize from Fourier transform to other signal processing. Yes?
If you see this yellow picture, what do you do with that?
If I see this yellow picture, what do I do with this? Well, I mean, first off, I say it's broadband, it's turbulent, it's chaotic. It has a different, fundamentally different than this one. The resolution here is not very nice, but it has some frequency peak behavior that might be useful. But it is a way of diagnosing kind of the evolution of this frequency spectrum in a way that's useful. There are also spatial modes. There are DMD modes associated with these as well that you could look at and analyze and ask a physicist about.
But what do you do practically with the spectrum? Do you then use it some predictions, or it's just for analyzing what the system is?
It's a great question. 10 years ago, our take was that the primary use of DMD was as a diagnostic tool because it was not very good for prediction, and it was especially not very good for control. The predictive capabilities have gotten better over time. And so, but I would say this is primarily a diagnostic tool. Okay, other things we can do. We very often have prior knowledge of physics. I know that my system has symmetries. I know that there's conservation laws. I know that's what I call partial knowledge of physics. And when I do these data-driven regressions, I would like to impose that partial knowledge so that the solutions I get have that partial knowledge baked in. And so this is a beautiful paper by Peter Badu from Cambridge on how to incorporate physics into the dynamic mode decomposition. And I'm just giving you one example. This is a very large paper. He has maybe a dozen different types of physics that he has shown how to systematically bake in to this DMD regression. But let's look at this. Where do I look first? Let's look here first. This is my data. This is a simulation of a quantum mechanical system, the evolution of a probability in a hexagonal potential. We have symmetry. Okay, that's a strong piece of information. We have hexagonal symmetry, but that's, let's say, all the information I know. If I look at the eigenmodes of this system, because it's a linear system, I actually can compute the ground truth eigenmodes for this hexagonal potential. And this is what you would get if you did a vanilla DMD with no prior information baked in. So kind of noisy, right? If you bake in the prior knowledge of a symmetry, you get this much cleaner middle row. That's the physics-informed DMD that Peter developed. Okay, so that's the big idea. Your data and your system has a symmetry. Doing vanilla DMD without that information, you are contaminated by noise. But if you bake in that symmetry, it strongly regularizes your problem and you find a much better solution to this ill-posed inverse problem. Now we're going to talk about the math. The vanilla DMD in red here is in fact doing a regularized or constrained regression problem. We're trying to find this A matrix that best advances my system one time step in the future. Y is just X one time step in the future. We're trying to find this A matrix that has a fixed or a minimal rank. That was the algorithm I wrote down in the morning. But there are many other constraints or manifolds that I can constrain my A matrix to be restricted to. I can restrict my A matrix to be only in the class of Toeplitz matrices, or circulant matrices, or Hermitian matrices, or whatever you know your symmetry is. You can say, I need A to be in that matrix manifold. And then this becomes a Procrustes optimization problem. We have dozens, about 60 known solutions for 60 known types of symmetries, how to restrict ourselves to that matrix manifold. And fortunately, they happen to be the ones that pop up a lot in physics. Things like, rotational symmetry and skew symmetry and things like this. So we have essentially a workbook, like a table of solutions of how to restrict my solution to different matrix manifolds that restrict my system to different symmetries. It's a big deal. Okay, this immediately lets you get away with noisier data, less data, and you get much more generalizable models when you bake in your prior knowledge of physics, which we almost always have. We know what class of problems we're solving. We know the general class of symmetries, even if we don't know the specific solution.
Do you have examples where you learn it?
We do have examples where we learn M. That's one of my favorites. Actually, that's my next slide. That's in this paper where Sam Otto, who was a postdoc with us before moving to Cornell, this paper is a beast. It's like a 90-page math paper. It's very, I think there's 4 people that read this paper so far. But essentially, he generalized this notion, not just linear regression, DMD, but any machine learning regression, any kind of machine learning model y-hat. How would you restrict your model to some, some manifold of solutions given by some symmetry? And there's this beautiful dual problem. If I know my symmetry, I can enforce it by constraining myself to be on this matrix manifold, or this manifold of solutions. For DMD, it's a matrix manifold. For machine learning, it's just a manifold. So if I know my symmetry, I can enforce it. But I very often don't know my symmetry and I want to learn my symmetry. And that's a kind of an interesting dual problem. So let's say I don't know the symmetry of my system. There are a few ways of learning the symmetry of your system. The simplest way of thinking about this is write down 10 candidate symmetries train 10 different machine learning models with those 10 candidate symmetries, the one that actually has the correct symmetry will generalize far better than the 9 that don't. Does that kind of make sense? Like, if I get the right symmetry, my model will generalize much better to unseen data. So you try 10 different symmetries, and the machine learning model that actually generalizes clearly captured the right symmetry. That's like the conceptual idea of what we do here. But what Sam showed is essentially, you can again write this down as a linear regression problem where we're trying to find a vector in a null space. We're trying to find the largest subgroup of GLN that my dynamics are invariant to. And that's a null space regression problem. And so Sam basically developed a bunch of algorithms to find the largest subgroup of GLN that your dynamics are invariant to, and that's your symmetry group. And we pose that as a well-posed regression problem. Yep, good question. Question, yes?
Yeah, so is the benefit of this that really just you're reducing the sample like size of your space you're trying to you're overfitting like.
Yeah, it's a good question. Like, what's the actual benefit? There's several tangible benefits that are really non-trivial, significant benefits. Okay, we're zoomed out of Koopman. We're talking about machine learning and regression models in general, like models from data that will fit the world. If I want to use my model for designing an airplane, it had better generalize beyond my training data. And it had better capture mass and momentum and energy conservation. So like your model needs to know that basic physics or it is not trustworthy in all of the scenarios in which it might be used. So learning and enforcing physics into these regression models is a safety critical issue when you apply machine learning to engineering systems. Like you need that to generalize. More than that, so that's a robustness and safety issue. More than that, I tend to be able to learn these models with orders of magnitude less data and noisier data when I get the right symmetry enforced. So it's also just a very practical problem is that we like to think of machine learning in the Google, Amazon, Facebook context of infinite data. But in most of our engineering problems, data is very expensive. One data point might cost $10,000. And so I only have a few data points I can collect. And so I need my models to be more efficient to train. So enforcing symmetries and conservation allows your models to generalize and be learned with much fewer, much noisier data. Those are like the most clear tangible benefits. Yep. Good question. Okay, I have 5 minutes left. Tomorrow, I'm going to talk about how we use more modern machine learning techniques like neural networks and autoencoders to learn these coordinate transformations. Remember, we were expanding phi in terms of a function basis, theta 1, theta 2, theta 3. We were like, doing a function approximation. Anytime you think, oh, I have a function approximation problem, it is now a neural network training problem because neural networks are amazing at approximating functions in the right setting. So that's what we're going to talk about tomorrow is how we use those techniques when we have high dimensional data. How do we learn these coordinates using neural networks? And the exact extreme opposite end, instead of having too much data where I need a neural network, what if I have very limited data? I have a point measurement of a brain or of a turbulent fluid. I have a single point measurement and I have its time series. How do I try to extract Koopman-y information, relevant information if I have way too little data? Way too much data, I use a neural network autoencoder. Way too little data, I'm going to use something called time delay embedding. Okay, so that's it for today. And tomorrow I will do that.